Hello, bonjour, it's Laura here. In this video, I'm going to talk about the strengths of acids and bases. So, let's explain what a strong acid is. So a strong acid is basically something that disassociates completely. So, for example here, these bars are indicating concentrations. So, and they're indicating a before and after. So this would be before, and this would be after put into water. So after a reaction. So this is the strong acid initially, so it's HA. So that's not really an acid, it's just, or an actual compound, it's just representing a strong acid. So in water, this acid is going to completely dissociate. So all of the hydrogens here are going to come off and then bind with the water to make the hydronium ions. So it'll all be H3O. And then the A here will be the conjugate base. Okay, so I'm just going to erase this stuff here because I've got a little picture to show you what that will look like if you could actually see molecules in beakers. Oh, and I'll erase this too. So this is the reaction that's happening. So the acid plus the water producing the hydronium ion concentration, which we know is acidic, and then the base. So this is what this looks like. There's equal amounts of the hydronium ion concentration and the conjugate base. See, so there's 4 of each of them. So that acid has completely broken apart. So say there were 4 acids to start, it's broken into 4 and 4. And so strong acids like hydrochloric acid or something, if you put that in water, all of the hydrogens are going to break off or ionize. Now, in contrast, this would be a weak acid. So again, we're starting with HA, it's just a generic acid, and putting it in water. So here you can see after the reaction, there's still a lot of that full acid. It hasn't ionized, it hasn't broken apart. So there are not that many hydronium ions here. So not the acid, the hydrogen hasn't come off of a bunch of these acids and joined with water to make hydronium. So the concentration is low here. And it's also low for the conjugate base. Not a lot of conjugate bases have been produced either. So here's an example of the reaction written out. And notice in this top one here, I just did a forward arrow to say that this reaction just goes forward completely. In this one, I've got a double arrow, and the arrow is stronger towards the reactants, meaning that the reverse reaction is actually stronger than the forward reaction. And actually, there's more acid still, like original acid produced, or more original acid that hasn't even broken apart. So this is what this would look like. So we've got a lot of this original acid, all the purple, and then just a few of the hydronium and the conjugate base. So what this means is it breaks apart. A weak acid breaks apart only slightly in water to form a solution of mostly molecules. So that means the acid has stayed as a molecule. It hasn't broken apart into ions. So when you're looking for strong acids, one thing you can do really is just memorize. There's not that many strong acids. And so here's a list of them here. Perchloric acid, sulfuric acid, hydrochloric acid, nitric acid. These are probably acids that you've heard of. And the interesting part them is that they have a weak conjugate base. So that means that the base is weak and it's not going to actually drive the reverse reaction to happen. So weak acids, there's a lot more weak acids than strong acids. So here's a list of them, and they usually have a strong conjugate base. So that means that the reverse reaction is happening more strongly sometimes than the forward reaction. So you can see that as the acid strength increases, the base is weaker, and as the acid strength decreases, their conjugate base gets stronger. So it's an interesting relationship. So here's a few other things to remember. So if we're talking about strong bases now, so not strong acids, but strong bases, they're usually formed from metals in the group 1 and 2. So an example, some examples would be lithium hydroxide, sodium hydroxide, potassium hydroxide, and calcium hydroxide. So these are all strong bases, and they all, just like the strong acids, they completely disassociate in the water. Weak bases are mostly the other bases. So if you look at a list and you're trying to figure out whether something is likely to be a strong base, look at the metal and see if it's in group 1 or 2. If it's not, then assume that it's a weak base. Now these weak bases disassociate only slightly in the water, just like the weak acids do. So here's an example, and you can see that you've got this double arrow again to show that the reverse reaction is actually stronger than the forward reaction. Okay, so that's a discussion of strong acids and bases, and the typical question that you would run into with these types of things is a multiple choice looking for which acid is most likely to be strong or which base is most likely to be strong. So you need to look at your list, or if it's a base, look for metals that are from group 1 and group 2, and that'll tell you it's a strong base. Okay, well done, Magwitch.